Hello everyone, welcome to the second lecture. In this video, we will cover some key concepts of big data platforms such as scalability, key processing models, and MapReduce. Okay, so what is a big data platform? Well, in the past, I'm talking about like 20 or more years ago, typically companies had different software or modules to analyze data, process data. So they were moving data around to each of those modules of software, and that was not convenient, especially if you have big data. That is not a good idea to be like shuffling around your data from one part to another. So the key concept of big data platforms is that it's a platform where you can store your data, and it's going to be like in the same place always, and then you can process the data where it is located. This has to be, it has to have some like key properties such as scalability. So you want to make sure that your design is going to, or your platform is going to be able to increase the capacities for storage, for processing, at the same time for analytics decisions in case you want to like create a model. So your platform it's capable to handle that requirement. Okay, so a big data platform pretty much has all these components in which typically traditional software cannot manage efficiently. Alright, so the purpose here is to provide scalable, high performance processing capabilities that support all the tasks that we want to make. Okay, so the key components, and I think we have already mentioned them, it's the storage. So we want to have like vast amount of storage to be able to cope with structured and unstructured data. So for that purpose, we will use a Hadoop distributed file system, which later we'll see is the HDFS. The processing part, in order to be able to compute like all the tasks that we need in a network. So for that purpose, in this course we will discuss MapReduce and Spark. Today, actually, we're going to introduce MapReduce. And the analytics part, remember the fifth B in big data, value. So once you have your data, you have the capabilities to process it. So it's important to start getting the insights from our data, applying some models, even some EDA, exploratory data analysis. So that's the analytics part here. Okay, just to give you some motivation about the importance of parallel storage and parallel processing. So imagine here we have two scenarios. So we have a single machine with 1 terabyte of data, and we want to transfer that data. So if we have a solid state disk, let's say that the typical transfer rate is 500 megabytes per second, maybe a little bit more, 600 megabytes per second, it depends. But let's say this is like the average value. So the time it will take to transfer 1 terabyte, it's around 35 minutes, maybe a little bit lower than that, 30 or more, 40. Now let's see the second scenario. So instead of a single machine, let's say we have a cluster with 100 machines, and our original terabyte has been split in the 100 machines. So there is 10 gigabytes in each of those machines. Therefore, the total transfer it's going to be like 20.48 seconds. So even though it's not efficient, like to use only 1% of the storage of each machine, this example gives us an idea of the importance of like distributing our data and the processing part. Okay, so the first key component is scalability. So what is scalability? It's basically the ability of a system to handle increasing amounts of data. So there are two types of scalability. So we can scale up, or we can go scaling out. So what's the difference between them? In scaling up refers when you get like more powerful hardware. So imagine that you have a laptop, for example, and you increase the capacities, like the storage capacity. So that's scaling up. While when we talk about scaling out or Horizontal scaling is when you get more machines. It's different. So it's important scalability because it depends on the context, of course. If the company does not have like big requirements of data, then it won't be a big deal, like it won't be necessary to get more machines and create a network. But if we're talking about big data, then scalability is a big issue. So we need to start thinking in architecture that reflects a little bit more the possibilities of scaling out. So this is how it looks, the scalability. So the scaling up, it's also known as vertical scaling. So here is not that we have 3 computers, no. It means that scaling up is like, okay, imagine that originally you have these capacities, but if you scale up, it means that you can either replace the machine or you can increase the capacity of the same machine, something like this, or even something like this. It's like we are increasing the storage capacity, the processing capacity, the RAM. In the case of horizontal scaling, it's when you add more machine. So originally maybe you have 1, but then you keep adding more, 2, 3, 4, 5, you keep adding resources. So that's the difference between scaling up and scaling out. One is vertical scaling and the other one is horizontal scaling. Now let's go into the details. So in scaling up involves improving the performance of a single machine, as we just mentioned. So we can increase storage, RAM, CPU. So the good thing about scaling up is like it's a simple model because there is only one machine. So the configuration, the maintenance, it's simple to keep. An example would be like, let's say we're gonna upgrade a server from 8 cores to 16 cores, and the RAM from 32 gigabytes to 100 to 28 gigabytes. So that's scaling up. So when to use, so it's suitable when there is a single machine and it can handle the load efficiently. So again, if the requirements of data and processing are not like demanding, so you should be fine with scaling up. There are some pros and cons. So we already mentioned some pros. Low complexity. Again, it's only one equipment or few equipment. It's consistent, so you don't need to worry about like all the problems that might have when you get a network, because you have to synchronize them. There is some latency issues. The cons, it's like at some point you cannot keep improving the machine. It means like it's way too expensive to buy or to get something above the standard. So there is no there is no benefit of that. I mean, maybe there is a benefit, but it's not worth the investment that you're doing. So that's the meaning of diminishing returns. So the cost, again, high-end hardware can be really expensive. So this is a big issue. There is a single point of failure. So if the machine fails, then the entire system goes down. So it's not resilient. So that's a big limitation. And scalability limits. There is a physical and economic limit to how much a single machine can scale. So there is a point where you cannot like keep improving what you have. This is when we are scaling up. Now, let's go in detail with scaling out or horizontal scale. Here, it involves adding more machines or more nodes to the network. So we are going to distribute the workload here. So the tasks are spread across the multiple machines. This is a nice property because now we have fault tolerance, because if one machine fails, then since we have a network, then other machines can take over and the system can keep working. So when should we use this configuration? So it's suitable for large scale applications, of course, of big data, cloud services, web applications where workloads can be partitioned. Pros and cons of scaling out. Well, scalability is a huge pro, because theoretically speaking, you can like add more nodes unlimited. So you can like keep increasing, which is a limitation in the scaling up. Cost effective, because typically when you get commodity hardware or standard hardware, it's less expensive compared to high performance machines. The fault tolerance part, which we already mentioned, so we're going to increase the resilience because if one node fails, the system can keep working. Some of the cons, of course, there is more complexity because now we need to manage the network, the distributed system. So there might be some issues, with, like with the data transfers and things like that. So we need to work more in the synchronization part and the network latency. All right, so that was about scaling up and scaling out. Now let's talk about shared versus distributed memory processing. So we have two scenarios here for the processing. The first one is shared memory processing. This is maybe like you have a single computer with multiple cores, and of course there is a single memory, and you can use the cores to access the memory and perform different tasks. That's shared memory because again the cores access to the same memory. Now the second alternative is distributed memory. Distributed memory is where you have like multiple nodes, like multiple machines. So in each machine you have memory and you have the processing unit. So this is distributed memory processing. Okay, so in shared memory, the processing model, you might have multiple processors. It's typically used when you have a multi-core or multi-processor system. There is a single memory space. All processors share the same memory. So applications, this is suitable for tasks that require fast access to share data, such as in-memory database, parallel processing with a single machine, and real-time applications. So this is when I have used this, for example, when I'm training a regression model, when I'm training a classification model in machine learning. So when you're doing the cross-validation part, sometimes you need to train the model in different splits. Like you have your data, and let's say when you do like 5 false cross-validation, so you need to train 5 models to compare them. So you can do that on parallel, like with the different cores. So that's an example of shared memory because you are in a single machine, but you have multiple cores. Now the pros and cons, but the pros, it's like you have faster data access because in the same machine. The programming model for the task is simple because there is only one equipment. You don't need to coordinate the network, so it's efficient. The cons, you have limited scalability because it's limited by the amount of memory that can be shared in the single machine. You can have some bottlenecks when the different processors try to access the same memory. All right, now let's talk about the distributed memory processing model. So in this one, each processor has its own private memory, and the processors communicate with each other by passing messages over the network. So this is when you have multiple machines. So in the architecture here, you have separate memory spaces. And the application, this is ideal for large-scale data processing tasks. So when you have big data, you want to split data, and you also want to process data independently in the different machines or different nodes that you have in your network. So of course the distributed memory processing model is the one that applies in that scenario. The pros and cons. Pros, scalability, for sure. Here you can keep increasing, you can keep adding more nodes to the network. Fault tolerance, if one node fails, then the system can keep working. And we also have mentioned that the cost effectiveness, because it's cheaper to add like more commodity software or standard equipment instead of a high performance single machines. The cons, of course, if you have like a distributed processing, so there is more complexity, network issues, and data consistency. All right, now let's talk about MapReduce. So MapReduce, it's pretty much a programming model for processing and generating large data sets with a parallel distributed algorithm on a cluster. So the whole idea of MapReduce is like you shouldn't worry about the processing part, about the assigning the task to each node in the cluster. The idea of MapReduce is like you should only worry about the things that you want to do. like the analysis that you want to perform. MapReduce is going to take care of the rest of assigning the jobs to each node and things like that. So it was developed by Google to handle massive amounts of data. And the most popular tool that uses MapReduce is Hadoop, Apache Hadoop, which we're going to learn in this course. So let me show you how it works. Let me give you an idea. Imagine that we have our data, that we have multiple documents with text. It can be millions of files, but let's say that we have four documents. Just for the sake of simplicity, but again, we might have millions of these documents. There are 4. All right. So then, imagine that the task here is we want to count words. We want to count the words in these files, right? So I'm gonna assign first the files to my nodes or machines. So let's say that we have here 2 machines. This is machine number 1. This is machine number 2. That's my network. It's a simple one, but the idea, can be extended to multiple nodes. All right. Then the data, it's assigned to the machines, right? Okay. And then we start mapping. That's the first part of the MapReduce process. So in the mapping, the idea is like we start. Remember, we want to count the words. So let's say that we're focusing only in two words: cat and dog. So in this machine, when these 2 files were analyzed, so the word cat occurred, let's say, 15 times. And the word dog only 5 times. Right? Now, similar idea, this machine is counting the number of times the word cat appeared. So let's say 25. And dog 10 times. So now we have these are the keeper values. That's how they're called in the map. So now we have counted each of these words, like cat and dog, but only for the first 2 files in the first machine and the other 2 files in the second machine. Now we have a process that is called shuffle and sort. So these key pair values are assigned to the machines again. They can be the same 2 machines or even 2 different nodes. They don't have to be the same. So this is one machine. It's another one. So for the first one, in the shuffle and sort, we send the same, of course, the same words. For example, cat and cat, and to the second one, dog and dog. So now each machine or each node is gonna reduce So in this one, we get cat, the sum of those 2, right? So that would be 40. So cat occurred 40 times. And in this one, dog is going to organize them and count them, so it's 15. And finally, you can get the output. So this is the map when you add the keeper values, and this is the reduce when you are adding the results, so to finally provide an output. So the whole idea of the MapReduce programming model is to assign the task, assign the jobs to the nodes in the network. So you don't have to worry about that. That's the premise of this programming model. You should worry only in the things that you want to do, how you want to map your data, what you want to do, which function do you want to apply here. In this case, we're just counting words, but it might be a different function that you want to apply to your data, a different analysis, right? So this is your concern, but the shuffles, the sort part, that's taken care by the MapReduce algorithm. Okay, so key components of MapReduce. So the map function processes input data, produces immediate key value pairs. That's what we did when we counted each word, the frequency. And the reduce function aggregates the intermediate key value pairs. That's what we did when we combine all the cats and all the dogs. So why it is important? The idea is that MapReduce simplifies the process of writing parallelized distributed data processing jobs because you don't care about that part. That's taken care by MapReduce. So developers will focus only in the core logic of the task. So in real world impact, let me tell you that the MapReduce idea was kind of like the standard. Like many years ago, it was the standard. Nowadays, there are like better algorithms. I have to say that if you check Spark, for example, typically Spark it's faster than the MapReduce of Hadoop. Even some authors have claimed that it's 100 times faster. So yeah, it's an optimized algorithm. So in general, you will see that Spark for this specific task, it's better. So these are the steps, which we already mentioned some of them. The splitting part, when we input data and it's split in smaller chunks, which are distributed across the cluster nodes. We did that with the files that were assigned to the machines. The map phase is where we perform the counting and we found the key value pairs. The shuffle and sort phase is when we kind of like put together the same key values and were assigned to a specific node or machine. The reduce phase is that when they were counted, aggregated, and finally is the output that we get, which was the number of cats and number of dogs in the documents. This is a similar example to the one that we just covered. So this is the input, this is our original file. So you have letters. Then we split the file. They are assigned, and then they are mapped. So in the first split, they map. Okay, they found 1A, 1B, and 1R, and similarly with the others, right? For example, with the third split, so it's 1A, 1C, and 1B, and then we put together the same. So A, you have two A1s, then B, B1, B1, C1, C1, and R1, R1, and then they are reduced, and when they are counted. So this is a similar example, counting words, which is by the way, that's a popular example when you're looking at big data and MapReduce. That's the most common example that you will see, like the one about counting words. Okay, so what are the MapReduce benefits? Scalability, because now you can work in parallel in a network. Fault tolerance, because you have multiple nodes. In general, it's simple and it's cost effective. So some real world examples. MapReduce is just Google used MapReduce. Actually, they invented MapReduce, and they use it for web indexing, and Facebook also to process the social media data. Okay, so the conclusions. Let's talk about scalability first. So when you're choosing the right scalability, it's not about like thinking that one of them is always better. It depends. So the choice between scaling up or scaling out will depend basically of the needs of your company. So scaling up, it's simple, but it's limited. And scaling out offers better long-term scalability for a large data set. So if you are in an environment where data is increasing at a remembered velocity, right? If it's really increasing with high volume, of course the scaling out will be your solution. But if you're talking about a small amount of data and it's not really increasing at a big rate, at a high rate, then scaling up will be your choice. So selecting the appropriate processing model, same thing. For a small to medium-sized task on a single machine, a shared memory model may be enough. Now, if we are talking about large scale distributed tasks, then the distributed memory model is essential. So you need to create the cluster with multiple nodes. And MapReduce rolling in big data. And as I mentioned before, it's like a foundational model. So it was like the key idea in how to process and how to assign the task to different nodes or different machines in a network. So it was the standard many years ago. Again, nowadays there are some like new technologies that are improving the performance, but still MapReduce is relevant from the technical perspective and even from a practical perspective. Okay, so this is everything in this video. I'll see you in our next lecture.